Welcome back to the lecture series in quantitative methods in chemistry. We are entering into the third week. The first week we saw how to quantitate concentration of different chemicals and different units that we would end up using. And in the next week we started to understand where do measurement uncertainties, how do they look in a data and how to understand them in terms of mean, standard deviation, and also how the uncertainty in each of the measurement that you might end up doing would result in an overall uncertainty in a final measurement. We also define terms like accuracy and precision that helps us understand what is the truth that we seek from the series of experiments that we end up doing. This week of lecture would be trying to understand where do these uncertainties arise from. It could be an experimental reason why it comes up, or it could be a random reason why it comes up. Here we will be trying to understand what are the characteristics of such errors and how they can be distinguished, how they can be minimized if possible. So in order to do this, why don't we start with an example. So let's take the example of something that we have done quite regularly in the initial part of this lecture. Let's talk about oxalic acid neutralization with sodium hydroxide. So you're going to form oxalates, and then water. Needless to say, you will have to balance the equation. That will end up becoming like this. So once you have a balanced equation, let's assume that we will be having this as the unknown. You will see as we go forward in the lectures that whenever you are doing standardization, you always have a primary standard versus secondary standard, NaO which is secondary standard. So therefore you generally standardize it against something that you know. And in this case you will be standardizing it against oxalic acid. And let's say that we need to prepare 0.1 normal oxalic acid in order to do this purpose. Let's say we will prepare 1 liter of it. So the first step of this endeavor will be trying to understand how much grams you would end up using. So let's quickly calculate that. Before going ahead, we would also like to remind ourselves of the relation between normality and molarity. Remember, the number of equivalents in this case would come up because of the 2 protons that get abstracted. So therefore this is going to be nothing but molarity times 2. So when you have something like this, this makes life a little easy. So basically you want to calculate 0.05 molar of oxalic acid. So with this being set, the next thing that you would like to do is how much should you weigh of oxalic acid in order to prepare a 0.05 molar solution in 1 liter. So in order to do this, all that you got to do is to do a simple math. So weight by molecular weight, which I am sure we remember is 63 grams per mole, times 1 liter of solution. So this indicates that weight in grams is going to be 0.5 times 63. That happens to be 3.65 grams. So if you dissolve 3.65 grams of oxalic acid in 1 liter of solution, you end up getting 0.05 molar oxalic acid, which in this context is 0.1 normal oxalic acid. Okay, now that we have seen this, you are able to recognize that there are 2 things that we are doing. One is that we have to measure out a certain weight of oxalic acid, and we have to dissolve it in 1 liter of a total solution. So a little bit of thinking makes you understand you have to use a weighing balance. Most often it's an analytical balance we use, which gives us very good precision of about 0.1 milligrams. But for the sake of understanding here, let's assume that the weighing balance that we are using has a 1 milligram precision. So therefore this is going to be nothing but 3.650 plus minus 0.001 grams. And let's assume once again for the sake of argument, the volumetric flask that you will be using has something like a 10 ml error that could come up. Okay, so now when you have something like that, you are going to have 1.00 plus minus 0.01 liters. So now what you are able to realize is that you need to combine the 3.65 grams in 1 liter of solution to get the desired 0.1 normal oxalic acid for you to perform this titration. So what you are able to realize, you are going to be dividing 3.65 divided by 1, And if you recollect the error propagation that we did last time, so this is going to be given by square root of 0.1 divided by 1 the whole square plus 0.001 divided by 3.65 the whole square. So let us quickly see what it amounts to. So this amounts to something like 0.001. Of course, this does not fully translate, so this is going to be equal to 0.05 times 001. This will be nothing but 5 into 10 to the power of minus 5. So which is going to be, okay. So this indicates the normality for this is going to be nothing but 0.1 plus minus 2 times of this, that will be 0.0001. Of course, this should not be written this way, you got to write something like this. This indicates once again that the lack of certainty comes from this value. Okay, so now that we have found this, let us go to the next part. With the normality defined at a certain level of precision to 4 significant figures. Now the next question is, let us say you are titrating 10 ml of NaOH. How do you get this NaOH? You generally use a pipette. And this pipette could also have an error associated with it. So let us assume this is a 10.1 plus minus 0.1 ml, that is the precision, sorry, 10.0 plus minus 0.1 ml precision that comes up. Okay. So now that you have this, the equation that governs the relation between these two would be V1N1 equal to V2N2. Let us say this is for oxalic acid and this is for NaOH. So what is this going to end up happening is that the normality of NaOH is going to be given by V2N2 by V1. And let us say now that you have pipetted 10 ml out, and what volume of oxalic acid was required, just for the sake of math, let us keep 10 ml of oxalic acid was required. So of course, and this will be measured from a burette. So far what all you have seen the use of 4 different pieces of instruments or equipment where apparatus, let us say, where you have used a weighing balance which has a certain precision that it goes with, a volumetric flask, pipette and a burette. Let us also assume here also it is a 0.1 ml precision that you have. So what ends up happening is that you have 10.0 plus minus 0.1 multiplied by normality, which is 0.1 followed by 3 zeros plus minus its precision divided by 10 plus minus 0.1. Of course, we are able to see the normality, it cancels out, it comes up to be 0.1 normal. Of course, this is not the piece of the exercise. What we would like to understand is what is the error or the precision that goes with it. So the N1, the sigma N1 is going to be given by N1 with the square root of 0.1 by 10, 0.1 the whole square. Since we are going to write it 2 times because of the numerator and denominator, we can as well put a 2 there, times the whole square. So now sigma N1 comes up to be 0.1 times 0.041. So finally you are going to get something like, sorry, point. So therefore the normality is going to be given as 0.100 plus minus 0.001. What you are able to realize is that depending upon the precision that each of the apparatus that we end up happening, the final precision is changing. Although you had a very high precision to start with, you are able to realize that an order of precision is being lost in the way that you are measuring the final concentration of N1. Of course, do not forget that this has to be back calculated into the number of grams of NaOH, and what is that going to involve is that this is going to come up as an error in the weight that you are going to end up measuring, that you might have ended up measuring to start with. So now the point is, what is the reason behind NaOH not being used as a primary standard is because it's extremely hygroscopic. So when you try to measure its weight during the process of weighing, it ends up absorbing a lot of water, which results in the concentration not being exactly what you wanted it to be. So therefore, this way of standardizing using something like oxalic acid, which doesn't suffer from such problems, helps you determine the concentration of NaOH which you might end up using for titrating against other acids. For instance, let's say you want to understand how much amount of phenol is being dissolved in water as a function of temperature, in which case as you change the temperature you will dissolve different amounts of phenol, then you will titrate it against the standardized NaOH in order to back calculate. So of course you must remember that this error that we have calculated here will propagate to the concentration estimation of phenol in this case. Okay, now that we have set the premise, meaning that every measurement that we might end up doing, every simple measurement, even in terms of weighing balance, taking it to titration, gives us this much amount of error. Let's go into the aspect of understanding where these arise from. So basically the term error is generally used by an analytical chemist in the context of measurement uncertainties. One has to remember, error doesn't mean the mistake that you end up doing, but the level at which we cannot be sure of a certain measurement that comes up intrinsically or maybe due to our own reasons. Most often these type of errors can be classified into these three major types. One is random error, quite a bit of which we saw in the previous week. We will be seeing more about it as we go forward. This is one error where, let's say this is a true value, you are going to have a distribution that comes across. This results in the spread across the mean value which you ended up measuring. On the other hand, you could have systematic errors. What do we mean by a systematic error is, let's say this is the true value that you are looking at, you did some mistake where you reproducibly did that mistake, where the true value and the measured value end up being subtly different between each other. On the other hand, you could also have gross errors which completely take the truth away from the actual value, which clearly indicating an outlier, and these are errors that can be easily figured out and minimized as you do an experiment. So let's start taking a look into more specifically how these errors are and what comes up. How do they come up? So if you take a look at systematic errors, there is always a cause associated with the systematic difference that comes in the way you are evaluating. And remember this kind of a shift. So let me draw the distribution again. Let's say this is the true value where you expect the true value to be in the line that has been drawn, and let's say the actual distribution comes across like this, whereas this is the measured value. Of course we always refer to the mean as the measured value. So the difference that comes up here could result in a biased way of analysis. You might start interpreting that this is indeed my true value, which is not the case. This is actually the observed mean of the sample that you have got. This is not even the population mean maybe. So in such cases what ends up happening, you end up doing a biased analysis. You might start to over-interpret. In this case, let's say this is the true value, you are overestimating x bar. On the other hand, if you have a distribution that goes like this, you might end up underestimating it. So basically all this results in a bias in your measurement and probably the analysis that you would end up doing as you go forward. But the good thing here is that these errors can be corrected in some cases to as minimum as possible. So when you pay close attention to where these errors could come from, these three are the major sources of such things happening. So one is the instrumental imperfections or instrumental errors that come up. The other could be methodical errors, which could be some of the protocols that are followed by the scientist, or it could be just personal errors that comes up from the bias of the experimentalist himself or herself. So as we just saw in a simple example where when you are titrating oxalic acid versus sodium hydroxide, you are able to realize just the glassware results in some error that could come up. Here in this slide I am showing some example of that. In this case what you are able to realize is that this glassware is optimized to work at 20 degrees Celsius, and the standard deviation that's associated with that would be 0.1 ml of this for this given glassware. On the other hand, if you take a look at this burette which measures 50 ml, you are able to realize the precision is about 0.08 ml at 20 degrees Celsius. Of course, not everything has to be prescribed at 20 degrees Celsius, but most often glassware do end up being prescribed to be used at that given temperature. So now what would happen if you do use it at a slightly different temperature? You are going to expect some volume expansion to happen that results in increasing the standard deviation for such measurements. So this is the case of a volumetric flask which also has a 0.8 ml on the 1 liter measurement. Of course, we assumed a 10 ml error that would come up. If you redo the math, you're going to have a lesser error in the sodium hydroxide normality measurement, but I just did that so that you understand how errors propagate and what could end up happening. On the other hand, the burette, once again as I said, also contributes to an error. This is an example of a measuring cylinder where you are also able to realize this has about 0.5 ml error, or rather 1 ml error for a 100 ml measurement that could come up, and this is also prescribed to be used at 20 degrees Celsius. So almost all equipment that you might end up using in the laboratory has a certain least count which comes up as an error. On top of it, you could also have differences that come up due to the apparatus itself. So it's just not the least count, but let's say you repeat the measurement enough, there will be a certain region of deviation that could come up, and that would result in an overall error. Okay, the weighing balance, as I said, could also result in an error. So what generally gets done is that these weighing balances, one would end up using standard weights that have a specific grams associated with them, which when calibrated against the weighing balance you end up using would help you ensure a less amount of error would come up in the weighing balance. And most often, as you are able to see a digital weighing balance here, the number of digits that they end up displaying indicates the uncertainty comes up in the last digit. If you pay close attention here, it also says the error is in 0.0001 gram, which is why 4 decimals are displayed in this analytical balance. So be very careful when you are using an analytical balance where the number of displayed digits could indicate the error that is associated with them, and there are some instruments where in the last digit they will end up underlining to indicate that that's where the uncertainty lies. So generally people tend to show the first digit that indicates the uncertainty, and this quite commonly is used across equipment. And on the other hand, you're looking at a pH meter here where 2 digits are indeed displayed. And how would you calibrate a pH meter is that quite commonly people use pH solutions, standard solutions across at least 3 different pHs, that is pH 4, 7 and 10, and you would be using the probe in the reference solution and using the same pH meter at, let's say, a given temperature, and then calibrate the pH. So this would ensure that as a function of pH, even if you are changing the temperature, you are carefully calibrating things across in order to ensure that whatever you are measuring is the right pH. In general, for pH, people generally give only 1 decimal, indicating that the precision exists within that decimal only. Okay, so now that we have seen instrumental errors that could come up, what other things could happen is that you could also have method errors that could arise. What do we mean by method errors? Let's say in the experiment that you're doing subtle mistakes that could end up happening. What do we mean by subtle mistakes? Is let's say that you have to do an equilibrium experiment, meaning that once you make up a solution, you got to wait for a certain amount of time before you can start doing the experiment. Let's say the rate kinetics are slow for the solution that you're preparing. What might end up happening? The equilibrium might not be reached, and you might start doing your analysis by then itself. So what could this result in? You could misestimate the equilibrium constant, which would in turn cause an error in delta G naught, and as you might fit this to other values, it would propagate to the other thermodynamic parameters. You might end up estimating using this parameter. Okay, that is one thing that could happen. On the other hand, what could also happen is that as you dissolve these chemical reagents, they might not be stable enough to reach equilibrium. So what ends up happening, as you prepare the solution, these species might end up becoming something else or actually disintegrating, where even before they reach equilibrium, you might end up losing them. Such experiments have to be very carefully set, and a protocol has to be strictly followed in order to ensure that reliable and repeatable and replicable measurements can be performed. On top of it, what could happen is that if you, let's say, wait long enough, it could be that you start forming side products for the chemical that you are using. So when this starts to happen, it might interfere with the kind of analysis that you're trying to do. Let's say that you're doing a fluorescence assay, and let's say the byproduct that ends up coming has a different fluorescence absorption and emission maxima. It could start interfering. Let's say that's close enough to the analyte that you're trying to look at, it will start giving you any biased results. Of course, in the instrumental error, I already pointed out to the fact that a weighing balance can be calibrated, a pH meter can be calibrated. What one could do is to come up with comprehensive methodology incorporating all this that could happen for an experiment prior to setting this experiment, that will help you minimize these errors that could happen. For instance, let's say that you know for a fact, let's say you're doing an adsorption experiment that takes an overnight to equilibrate. It's always a good idea to start your experiment a day earlier and get this going. On the other hand, let's say that you are trying to do a kinetic experiment where the starting material will change very quickly. You need to learn how to minimize the dead time, meaning that when you start the reaction kinetics in the vessel and the time from which you actually start making the measurement. There could be a difference between these two times, which is called as the dead time, and this would influence the final results that you might end up getting. So therefore, minimizing dead time in a kinetic experiment is important, while making sure equilibration happens in a thermodynamic experiment is extremely important. Now, coming to the final point that might that will help us conclude the systematic errors, you could also have personal errors that could come in. What do we mean by personal errors? It could be that a person is trying to do a titration where the indicator that you end up using actually gives a color that this person is not perceiving it due to whatever problems. It could be that it's a color change that happens between green to red in a fluorescence experiment where this person is not able to see, probably because this person is color blind. Or what could end up happening is that when you have a burette, when you are trying to make a reading, you might make a mistake where instead of reading the lower meniscus, you end up seeing the upper meniscus. Of course, whichever has a different meniscus, opposite meniscus, you will start seeing the upper meniscus, but in general cases you will have to see the lower meniscus that comes up. Or on the other hand, you could also perform a personal error where if you are using the burette, the last portion of the burette, which does involve a certain amount of volume, is not properly used in the first step, meaning that when you are filling the burette, you might not have filled the bottom part, and when you are titrating, the volume change would be higher, indicating more concentration of the analyte that you are trying to look at. That could also be personal error. On top of it, let's say you are looking at the burette, and instead of looking at it at the eye level, you might be looking at it a little lower or a little higher instead of looking at the straight eye level reading. So what might end up happening, you might have an error that comes up basically in the way you read out a given value. All these contribute towards personal error. And one thing that is very important to understand here, not just this, there are some biases that comes up with an experimentalist, because most often when you are doing science, when you are setting up a hypothesis, you already have a preconceived notion towards what to expect. But remember one thing, the moment you start expecting something, you become a biased researcher, and many times this ends up happening when we are setting up an experiment where you expect a value to come off, and when you're doing a titration close to that value, you're very careful, but any value ahead or later than that, you might be a little careless. And this could happen in a way where you're expecting a higher value and you titrate it all the way just to see that the color change has already happened. So these kind of personal errors can be avoided by carefully following a protocol and doing things in a systematic and unbiased fashion. Okay, so now that we are done with this, let's take a small look at what type of errors could come up when you're using different equipment. So let us say in this case where you're trying to make weighing balance help you measure some amount of oxalic acid. Let's say you want to measure 3.65 grams of oxalic acid, and let's say the actual reading that comes up is 3.95 grams. So now the question that comes up is that, oh, there's a 0.3 gram difference. So does it mean if I weigh 4 grams, will it weigh 4.3 grams? Or maybe there is a slope that is associated with it, meaning that as I keep increasing, when I go from here to here, it need not be 4.3 grams, it could be little more than 4.3 grams or little less than 4.3 grams. So this is basically something like a calibration graph, where if you add a known amount of grams and if you are able to measure it and then you try to get a correlation between these two, this is like known weight, this is the measured weight from your analytical balance, for instance. Then you get points which you can fit, and then let us say there is an intercept that comes where the slope is equal to 1, but the intercept comes as something. Let us say the y in this case is x plus c, where the slope is 1. The c indicates there is a constant offset that comes in measurement. If there is a constant offset, what is going to end up happening? Be it 3.65 grams when you measure, it is going to be 0.3 grams higher, or if you measure 4 grams, it is going to be 0.3 grams higher. Even if you measure something like 15 grams, it is going to be 15.3 grams. On the other hand, it could be the case where you are having a slope that comes up. So what happens with this slope is that as you keep increasing the weight that you are going to measure, you could have a more estimation or less estimation depending upon the slope that you are having. Let us say you have a 1.1 times x, what is going to happen? You are going to have a 10% error that is going to be associated as you keep on weighing more. For instance, when you weigh something like 10 grams, you are going to get 11 grams. When you are going to weigh 100 grams, you are going to get something like 110 grams. So what ends up happening? Here it is a 1 gram error, while here it is a 10 grams error. So you are able to realize that it proportionally keeps increasing, while on the previous example, be it 10 grams you measure, you are going to get 10.3, be it 100 grams you measure, you are going to get 100.3. This indicates there is a difference between constant error versus proportional error. On the other hand, you could have cases where you are having the case such as m prime x plus c prime, where there could be a slope and an intercept associated, where one has to be extremely careful, and these are the reasons why one should always calibrate an instrument before ending up using it for any experiment. So calibration for different experiments is an extremely important step in order to get as reliable values as possible and minimize systematic errors that could come up. Alright, so now we would stop this lecture here and we will continue with understanding other ways to determine what kind of errors exist and what are random errors as we go forward, and we will also take an example of how this works out in an experimental scenario. Thank you.